Hello everyone and welcome to lecture. Today we're going to continue on with our first order theory, and we'll talk about a number of different topics for finishing up the sections on first order differential equations theory. Many of the things that we'll be studying today and talking about in today's lecture we're going to expand upon and extend to the higher dimensional case for systems of first order ODEs. So essentially in today's lecture we're going to be studying certain ideas and topics that will later extend to higher dimensional analogs based on the ideas that we'll be developing here. So it's really important to kind of understand all of the ideas in lecture today. And the first thing we'll be talking about is the simplest form of a first order ODE, which is called an autonomous or not depending on time. By time, it could mean that whatever the parameter, the independent variable is for the ODE. And an autonomous first-order ODE is one in which the function f of x comma t on the right-hand side does not depend explicitly on the independent variable t. And we're going to be using y here instead of x for our solution, which is typical of what we were doing in the last lecture. So for example, y prime is equal to just f of y. There's no explicit t dependence on of the function f on t. So if this is the case, then we call this first order differential equation autonomous. And I want to note here, because this will be important later on, if a first order ODE is not autonomous, so f does depend on t explicitly, all hope is not lost. We can actually define an autonomous system of differential equations, which is very, very cool, and we'll see many different applications of this in the future. So specifically, even if we have a single first order differential equation that is not autonomous, we can set xi equal to the vector yt. Right, this is the definition of xi. The vector xi1 of t, xi2 of t. And then this vector xi, when we differentiate it with respect to time, because it's a vector with two components that depend on time, the derivative of this with respect to t, we call it xi prime, is going to be equal to y prime, and the derivative of t is 1. So this will be equal to f of y comma t 1. And this itself is some new, it's a vector function of xi, because if xi1 is y and xi2 is t, this is just f of xi1 comma xi2, which itself is purely a function of xi. This is a vector function of xi. Call it g. G is a vector function of xi. And you see now this this is a first order system of two differential equations, but this system is an autonomous system of two first order ODEs. So even if you have a non-autonomous system, you can, by adding a first-order differential equation, you can express that as an autonomous system of first-order ODEs. And we're going to see this applied in depth when we deal with more complicated non-autonomous systems of ordinary differential equations. This idea can be extended directly to systems, which is very cool. But even for a first-order ODE, we can express it as a non-autonomous first-order ODE as a system of two first-order autonomous ODEs. And I also want to note that both of the population models, the basic population models we've talked about before, are autonomous. This is the Malthus and the Verhulst models. And these are the most basic form of those models. We'll see a more generalized form today that is non-autonomous, that is sometimes better to use in certain scenarios. And so the first theorem that I want to present today, and this is specifically for autonomous differential equations, is a sort of shifting theorem. Which says that if we have a solution of the first-order differential equation, that's an autonomous first-order differential equation, we can shift our solution. So the theorem says that if y is a solution of that autonomous first-order differential equation on some interval from A to B, where A is, as we talked about in the last lecture, then for any constant value tc in this interval, the function defined by y of t minus tc is also a solution of the differential equation on the shifted interval from a plus tc to b plus tc. And the proof of this is rather easy to go through and do. You just need to take the chain rule and apply the chain rule to the function f of t. But this is going to be important in a little bit later on in some of the later proofs that we'll do for such differential equations. And the next thing that I want to define, I want to specifically define what's called the orbit of a differential equation. So we're going to let phi of t, and phi of t might also specify some initial condition, why not, or y1 even. So we can kind of be free with how we denote that. We'll call it y1, be a solution of star with some maximal interval of existence. Alpha to omega, which we talked about at length in the last lecture. And the set of values of the solution, phi of t, we don't have to specify the initial condition right here, at least not right yet. So the set of values of the solution for all t in the interval of existence is called an orbit of the differential equation star. And it's important to note that in general, an autonomous ODE will have multiple orbits. Another very important definition that we'll have to make is that of an equilibrium point. And in general, a point y naught is an equilibrium point or a stationary point of our differential equation if the value of f at the point is equal to 0. Sometimes called a stationary point, because if the value of the function f at some point y naught is 0, that means that dy dt is 0 at that point. So it turns out that these stationary points are really, really important for determining the qualitative behavior of solutions. Additionally, we also say that, so if in addition, there exists some positive delta greater than 0, where delta is a real number, such that f of x is non-zero for all y, or f of y is non-zero for all y such that y minus y naught is less than delta and greater than epsilon. So the function is non-zero for all y around y naught in a small enough region around y naught. And we say that it's an isolated equilibrium point. Which is a special, more restrictive type of equilibrium point. So just in pictures, this means that if we have a line for y right here, and y naught is right here, what this is saying is that if there exists a region, a small enough region around y naught, from y naught minus delta to y naught plus delta, where there's no other equilibrium points in that region, so delta can be as small as we want to, we call it y naught an isolated equilibrium point. And this will be a very important idea. So what we're going to see is that we can qualitatively classify the behavior of differential equations by finding these equilibrium points and then determining how the solution should behave around the equilibrium points. So let's look at a couple of examples to see what an orbit of a differential equation looks like. For the Malthus differential equation, or the exponential growth differential equation, recall that this is a population model, and when we non-dimensionalize, we take y equals population over the maximum population, and tau is equal to r times t. And the differential equation that we get is dy d tau is equal to y, which when solved gives us, when we solve this via, gives us a separable ODE, indicating that this is equal to tau plus c which then leads us to the absolute value of y being equal to the absolute value of y naught times e to the tau. And we can go through and find the dimensionalized solution of this in terms of population, like we showed last lecture. But the main idea here is that this is giving us 3 possible orbits, or 3 possible solutions to our ODE. Specifically, we have a solution for negative values of y. We have a solution for y equals 0. And we have a solution for positive values of y. And when we're modeling a population, the only real, physically sensible requirement is that y is positive, the population is positive. However, in terms of the differential equation theory, there are actually 3 possible solutions to this ODE, which each correspond to a different possible value of y. Right? This equation right here is satisfied if y is less than 0. It's the equation y is equal to negative absolute value of y naught e to the tau. Well, if y equals 0, which is constant at 0, and if y is positive, we have the solution y is equal to positive absolute value of y naught e to the tau. And we can visualize these 3 solutions, or these 3 orbits, using what's called a phase line diagram. And we'll see that this is one of the big concepts that we'll be able to extend to systems of 2 differential equations as well. But to draw a phase line diagram, essentially what we have to do, and by the way, this does not require us knowing the solution a priori. We don't have to actually solve for the differential equation to draw the phase line diagram. The first step is to calculate the critical points, which we can do without, or the equilibrium points, I should say. And we can do this without going through and solving the ODE. So recall that even before solving this ODE, the equilibrium points or the EP, which I'll abbreviate as EP later on in the lecture, are when f of yt equals 0. So for this function, it's when y equals 0, which means we have 1 equilibrium point, and that equilibrium point is at 0. And thus the orbit sets, or the orbits, are split into the 3 parts, for the 3 main parts for this solution. The first orbit set is from negative infinity to this first critical point, or this first equilibrium point. The second orbit set is 0. And the third orbit set is the interval from 0 to positive infinity, where from negative infinity to 0, this orbit set is characterized by the solution negative absolute value of y naught e to the tau, which as tau gets further and further and further, is moving further and further and further away. As tau increases to positive infinity, e to the tau is getting larger and larger and larger. So these phase line diagrams, we draw arrows on to indicate the direction of the solution at every given point. Similarly, for the other solution, or the solution corresponding to this orbit set, for any initial condition here that's in this orbit set right here, the solution is going to head out to positive infinity. Because the solution is characterized by absolute value of y0 times e to the tau. And the solution corresponding to an initial condition in the middle orbit set of 0 is just going to be 0. It's going to stay put at that equilibrium point. We'll see later on how to classify equilibrium points. Equilibrium points can always be classified, but this is going to indicate later on when we define it that 0 is actually what's called an unstable equilibrium point. So I want to note here that the arrowheads above, represent the qualitative behavior of solutions with initial conditions in the orbit set. And this makes a lot of sense here. We can make even more sense if we go forward and maybe do a plot of the exact solution here to see how the solution to this differential equation is behaving. So recall that for the exponential differential equation, we get in general, depending on where the IC is, two different orbit sets. The first orbit set is from 0 to positive infinity in y. The axes here, this is the t-axis, and then this is the y-axis. And the solution, if we have an initial condition at t equals 0, starting right here, say, and this is y0 equals 0.45, we're going to shoot off to positive infinity for positive t as t goes to positive infinity. If instead we have an initial condition in the orbit set from negative infinity to 0, just from here to here, the solution is going to shoot off to negative infinity. And if we have an initial condition of 0, the solution is just going to be the constant y equals 0. So this is what is meant by what we just did with our orbit sets. We have multiple different possible orbit sets that the Malthus equation solves in general, in its most general form. So let's take a snapshot of this, put it in the notes. So the next main example that we considered was the logistic equation, logistic growth. So this is the next differential equation that we'll look at. And what we're seeing here is that phase line diagrams are a simple geometric device for analyzing the behavior of solutions to ODEs. These are very, very important. And understanding these are very important because later on we're going to study higher dimensional analogs based on these diagrams. So it's really important that you understand what they mean and how to go through and understand these diagrams. So the Verhulst population model, once it's suitably non-dimensionalized with y and tau, is just dy d tau is equal to y times 1 minus y. And I'm not going to rewrite the non-dimensionalization because it's the same as for the Malthus model. And remember that when we solve this, we end up getting the natural log of absolute value of y over 1 minus y is equal to tau plus c when we separate variables here and we solve the differential equation. This then leads us to conclude that the general solution to our differential equation is of the form y over 1 minus y is equal to the absolute value of y naught over 1 minus y naught e to the tau times e to the tau. Which, when we went through and solved it, the population model, we were able to make an assumption about y being positive and being between 0 and m. But this general solution is actually has, it's getting more information here. Specifically, right, from this differential equation right here, we can conclude that we're going to have multiple different orbits. We'll have orbits or solutions to our differential equations when y over 1 minus y is less than 0. We'll have orbits when y over 1 minus y is equal to 0. And we'll have orbits when y over 1 minus y is greater than 0. So we look at what this is telling us. Well, one way that we can have this be true is if y is negative or less than 0 and 1 minus y is positive. Another way we could have this be true is if y is positive and 1 minus y is negative. But you might immediately see a problem with this. In order for this to be true, y would have to be greater than 0 and 1 would have to be less than y, which is a contradiction. So we can't have this be true. This is only satisfied when y is equal to 0. So the third possibility is that this has to be greater than 0, strictly positive, which will happen when either y is greater than 0 and 1 minus y is greater than 0, and when y is negative or less than 0 and 1 minus y is also less than 0. So it looks like this is giving us 4 possible orbits, and sure enough, this is exactly what we have. If you look at the phase line diagram for this scenario, this system, we see the following. So we're going to break this up into 4 parts, and it turns out we actually have one extra orbit here that we're not recovering Well, I'll explain this in a second. So our main cutting up of this scenario is from 0 to 1, or main cutting up of the phase line is from 0 to 1. And when y is less than 0, the solution is going to be decreasing. Exponentially, according to that logistic function that I didn't write down the exact solution, but I did write down, I guess this is technically the exact solution. So it's going to be going down like this, and you can write down the relationship exactly. It'll be y over 1 minus y is equal to negative y naught over 1 minus y naught, absolute value of this, times e to the tau. And you can go through and solve for y in this if you want the exact expression for the solution. What we solved for when we did the Verhulst population model was for our initial conditions from 0 to 1, because these corresponded to the physical scenario that we were talking about. And on this solution, or on this interval, we have an exponential increase up to up to 1, which is the maximum population level. And if you continue to kind of go on and look on this for initial conditions above 1, you have that the solution will decrease down to this value 1 right here. And so the orbits for this ordinary differential equation are the sets from negative infinity to 0, the set containing 0, the interval from 0 to 1, the set containing 1, and the set from 1 to positive infinity. So we actually have 5 orbits for this ODE. And this can be seen without even going through and getting the solution to the ordinary differential equation, just by looking at this function right here. You consider the function on the right hand side of the first order ODE. This function has zeros when y equals 0, and it has a 0 when y equals 1. So if the initial condition is either 0 or 1, the derivative is 0 always, and therefore the orbit is just the constant value 0 or the constant value 1. But if you take an initial condition that's a little bit less than 0, the solution is going to go off negative infinity. If you take on the interval of existence for solutions that are on this orbit, you take an initial condition that's inside this orbit, the solution goes up to 1, a limiting value of 1. And if you take a solution in this orbit right here, so an initial condition anywhere in this interval, it's going to, in the limit, tend to the value 1. So if we, just like we did for the Malthus equation, take a look at a plot of this, these solutions, the solutions really are behaving exactly as we would expect. for a given initial condition, y naught, we have exactly what we would expect here. And if we go through and change our value for y naught, you see that you get exactly what you would expect here. So for any given value of y naught in this interval right here, you get negative y naught. The solution is going to, so you start in the interval from 0 to negative infinity for your initial condition. The solution goes down to negative infinity. If you start with a value for y naught inside the interval from 0 to 1, the limiting value is 1. And if you start with an initial value inside the interval from 1 to positive infinity, the limiting value is also 1. And then our two other orbits are, if you start with the value, this is the solution value. Our two other orbits are, if you start with a value at 1, the solution is constant at 1, it stays constant at 1. Or if you start with a solution value at 0, the solution again stays constant at 0. So the important takeaway here is that to figure out the orbits of a given ordinary differential equation, we don't actually need the solution. The solution does help to verify and give us a good idea of what we're predicting is correct. But we can go ahead and directly just kind of see, just using the function on the right hand side, what the orbits are going to be for a given differential equation. And this is very, very, very useful. And what's even more useful is going to be the extensions of this to systems of first order differential equations. So we can also go through and prove some theorems about orbits. I'm not going to actually prove the theorem, but the main reason I introduced the shifting theorem before is that we can prove the following. If the function on the right hand side of the differential equation, or f of x in star, and let me open up the notes here. So if the function f of x is differentiable continuously, so if it's continuously differentiable, then the orbits, any orbits, are either disjoint sets or identical. So the same set. And this is what we've seen in all the examples that we've talked about so far. The proof of this isn't really that difficult, so I'm going to leave it for you to go through and prove on your own, or to go through and it's all of the proofs that I'll talk about are in the Kelly book, so our course text. It uses the previous shifting theorem. And the extension of the idea of orbits to more complicated systems is something that we'll focus on a little bit later on in the class. And using orbits to really understand the behavior of differential equation solutions. The phase line diagram is for some two-dimensional differential equation, or two differential equations. It's called the phase plane. In more general systems of differential equations, it's known as the phase space of the system of differential equations.